So, just to recap what we talked about on Monday, there's not really a big geologic hydrogen industry right now, and it's actually not even really clear what the total resource potential is or the best way to explore for geologic hydrogen. So there's a lot of unknowns, but it's an emerging area, and it's kind of exciting because it's early times here. And the nice thing about geologic hydrogen is if you compare the value chain here, you simplify, and remember, well, I can pull up the version of this that has to do with, yeah, okay. So here's the energy value, the hydrogen energy value chain. You see there's all this complication around the supply and then the handling of it. Now, if you can find geologic hydrogen and produce it the way you would natural gas, then that simplifies a lot of the stuff here on the left-hand side and in the middle, because now, if I go back here, you just have your supply, which is the subsurface, and then you handle it the same way you would handle natural gas, and you can get it to your end user. Okay, so again, the best known example of production of geologic hydrogen is this Barakabugu in Mali, which is a place where it's a village where they're producing hydrogen, which then they're using for power in the village. And it's kind of an odd occurrence because it appears to be continuously recharged. They don't see a decline in production rate or reservoir pressure. So it's not entirely sure what the source of the hydrogen is and how long they can expect that source to persist. But it's, this is the one when you Google geologic hydrogen, you usually find it. More recently, this is a publication from last, I think it came out last spring. It's a mine in Albania. And I'm not even going to bother trying to pronounce that because I don't speak Albanian. But they had they published the statistics of the flow rate here in this mine. And it's flowing about 215,000 cubic feet a day of hydrogen. And it's a chromium mine, and importantly, it's drilled into a type of rock called an ophiolite. We'll discuss what that is in a minute, but ophiolites are a class of rocks that are called ultramafic rocks, and their mineralogy is such that under the right conditions, they can produce hydrogen as a result of a chemical reaction called serpentinization. So we'll get to that in a minute, but that's what's important about this. And it turns out, going back to 1992, they've had 3 major explosions here because of the hydrogen. But basically, they believe that the mine has intersected a fault zone, which is acting as a conduit for hydrogen coming from somewhere else where it's being generated. And it comes up here and exits out to the atmosphere. So again, kind of an odd occurrence. And here's another one. This is a hydrogen seep in Turkey, and it isn't pure hydrogen. It's mostly methane, but it's fairly enriched in hydrogen, and it's just got this continuously burning flame. And it is believed that this was the source actually of the first Olympic flame back in the original Olympics back in ancient Greece, which is kind of cool. And this one is also associated with these ophiolite rocks. So there's some association of hydrogen and ophiolites and serpentinization that, I think that's what's causing the generation and the accumulation. But when you start looking for hydrogen, you notice that it is actually everywhere. This is a map of reported discoveries of methane in gas wells at abundances above 10 mole percent. And you can see that they're globally distributed. this paper by Zagonic in 2020 was kind of an interesting paper because he works in France, but he is Ukrainian, and so he speaks Russian. And there's an interesting kind of bit of history here. You'll notice a lot of these reported occurrences of hydrogen are clustered around Russia and Eastern Europe. And it turns out the reason for this is that the Soviets, back during the Soviet era, had this idea that natural gas was actually produced abiotically very, very deep in the earth. And so they drilled all of these like super deep boreholes trying to find, the source rock for natural gas. And they, in the process, found a whole bunch of hydrogen because they were drilling very deep into the crust. And so you just don't see that in other parts of the world because people weren't out like drilling very deep holes into the crust and reporting how much hydrogen there was. Anyway, so Zagonic was able to go back to primary sources that were in Russian and actually report, quantify and report where these things were. So that's a long way of saying that there's probably a fair amount of sample bias in this distribution of hydrogen. And you'll notice, for example, there's no reports in South America. I guarantee you that you can find geologic hydrogen in South America. It's just probably for lack of looking. So it, basically everywhere you look, you can find it. The reason that we don't typically talk about it in the context of conventional natural gas production is really just because it's typically not monitored for during drilling. So when you're drilling a gas well or an oil well for that instance, you have a gas monitor, it's called a hot wire, and it measures the amount of methane, ethane, propane, and butane coming up in the drilling fluid. But that type of equipment does not monitor hydrogen. So it's not clear when you're drilling a natural gas well whether there's any hydrogen in it. You might have some, not even know about it. So it's kind of some interesting things. Okay, so what is the source of geologic hydrogen? Well, it could be a number of different things. Serpentinization is the easiest one to understand, and that explains why geologic hydrogen is often associated with ultramafic rocks, because that's where those chemical reactions occur. But there are other things that can happen. So radiolysis of water deep in the crust. So this happens when naturally occurring gamma ray emitting elements, so namely potassium, uranium, thorium, we talked about those in the context of geothermal heat. Those gamma rays can actually split apart water and leave you with oxygen and hydrogen. So that's another possibility. And then there's some evidence that there could be a deep source of hydrogen somewhere in the mantle or the core somehow. It's still a little unclear what that would look like and how much it would be. But there's been some interesting papers published recently that suggest that the lower mantle could actually contain a significant amount of hydrogen. Now, we're not going to drill down there, but some of that hydrogen can diffuse up into the crust and possibly accumulate. Okay, so we'll talk about serpentinization because that's maybe the most promising source of recoverable geologic hydrogen. So ultramafic rocks contain a large amount of a mineral called olivine, and it is a solid solution magnesium or iron silicate, okay? And under reducing conditions, the iron will react with water and it will produce iron oxide, silica, and hydrogen. So that's the serpentinization reaction. And it happens between 200 and 315 degrees Celsius. And the special conditions are that the water has to be undersaturated in carbonate because the carbonate actually competes with or basically interferes in this process because it competes with the water for this reaction. So if you have the right conditions, you can have the serpentinization happen and it can produce hydrogen. So where can we find olivine? Well, it's found, like I said, in these ultramafic rocks. Okay, so this is a diagram of igneous rocks, and it's kind of funny. I don't often find myself talking about igneous rocks. It's usually sedimentary rocks. But the classification of igneous rocks depends on the mineral composition. So over here, the boundary between granite and diorite, that's typical granite that we find, for example, in New Hampshire, which is where I'm from, the Granite State. But ultramafic rocks are way over here on the very high olivine end of the spectrum. And so there are rocks like peridotite, serpentinite, or excuse me, ophiolite, that sort of thing. So if we're looking for peridotite that is enriched in olivine, we want to look somewhere where the upper mantle has been exposed somehow or is present in the subsurface for some reason. And so peridotite occurs in the upper mantle. So the way when you cut through the crust, you've got the crust on top, and then the mantle is right down here underneath this thing called the Mohorovicic discontinuity. And that's the peridotite right there. So it's going to be close to the surface near mid-ocean ridges, where actually at mid-ocean ridges you have reactions with seawater that actually serpentinize the upper mantle right there. But if you're looking for this in the subsurface as a source of hydrogen, you might look somewhere where you've got an ancient rift or an ancient mid-ocean ridge that's been buried and it's reacting with water. And in particular, it's easiest to find where the crust is very thin, because to get to the peridotite, you have to drill through the crust. Typically on continents, the crust is about 35 to 50 kilometers thick. So that's very thick. You're not going to drill that far. So you've got to find places where, for whatever geologic reason, it's close to the surface. Okay. So ophiolite complexes are a sequence of igneous rocks that form when you have, for some reason, oceanic crust and associated upper mantle that somehow get uplifted and placed onto a continent. That's called a process called abduction. This is where you can often find peridotite at the base of this ophiolite sequence. And ophiolite comes from the Greek word for snake, ophis. And serpentinization obviously comes from the Latin word for snake, serpens. And they're called this because when the peridotite gets serpentinized, it develops a texture that kind of looks scaly, like those are petrophysics students. They're excited to see me for some reason. It's got a kind of a scaly appearance, like a snake skin. So that's why we call it that. So one easy way to explore for hydrogen is to find ophiolite complexes and drill into them. And this is a map of ophiolite complexes that we know of around the world. And you can see there's a pretty large number of them. There's a significant amount over in the Eastern Mediterranean region due to the kind of plate tectonics that they have going on over there. But there's some in California, Southeast Asia. So, there are places that you can go and find these things and maybe try to drill into them. That might be a possible way of exploring for hydrogen. Now, it can be difficult to know where exactly you want to drill because, with oil and gas, a lot of early exploration focused on drilling where there are active oil seeps or gas seeps, right? So there's, companies maintain these big seep databases for like the Gulf of Mexico and other parts of the world. So you can figure out, oh, maybe I want to drill here. But the thing with hydrogen is that you can't see it, you can't smell it. And if you're not just going to be wandering around with a hydrogen detector, right? You're not going to measure it if you don't expect to see it. That's the problem I was talking about earlier with why we don't see it showing up in a lot of natural gas wells in the US is because we weren't looking for it. That doesn't mean it's not there. And like I was saying earlier, these hot wire systems or gas chromatographs that measure for the presence of hydrocarbons, they use hydrogen to carry the gas sample. And so they're specifically designed not to see hydrogen. So you need to use a special hydrogen detector. So it can be very difficult to prospect for hydrogen, but there are a couple of interesting features that you can use to try to find hydrogen. And one example is these features that are known as either fairy circles or Carolina bays sometimes, but they are these circular features which can be a couple of meters in diameter. This is a picture from Namibia, I believe, or up to, a couple of kilometers. This is these circular lakes in eastern North Carolina. That's why they're called Carolina bays. But these features have been found to be associated with surface seepage of hydrogen. So here's a couple of papers looking at, this is a Carolina Bay in North Carolina. So this one actually isn't filled with water, but it's a circular feature right here. And what they did in this paper was they did a bunch of measurements of hydrogen seepage in and around this particular Carolina Bay. So in this figure, the circles are sized relative to the hydrogen concentration that they measured. Okay, so you can see that near the boundary of the Carolina Bay is actually where you get the highest hydrogen concentration. And if we look at a transect across here, you can see that you reach the highest concentrations right near and just inside the circle, and then same thing on this transect over here. So there's, something's going on here. There's also, here's a study from Western Australia and a fairy circle, and here's a fairy circle in Mali, again, looking at hydrogen concentration. So there's definitely an association between these features and the seepage of hydrogen. And, when you start looking for fairy circles or Carolina bays, you notice that there's actually a ton of them out there. So North Carolina, for example, this is a map of Carolina bays, and they're outlined in yellow. You can see all the way up here. So this roughly corresponds to the fall line here, where you've got the Paleozoic rocks exposed to the surface, and then this is the coastal plain. And right, along the coastal plain, they're kind of all over the place. So there's potentially a large source of hydrogen somewhere under eastern North Carolina. So, you might think about drilling there. I don't know. It's not entirely clear, again, what the source is. And I don't have additional slides on this because I actually have an entire 45-minute webinar on geologic hydrogen, but I'm not going to bore you to death with that. But the one of the big questions is, does hydrogen accumulate